Hello everyone, welcome to this lecture. I am Amlan Das. Today I will discuss about Laues equation of diffraction. Okay. In Bragg's law, we see that incident X-rays are scattered by planes of the crystal. But in Laue treatment, X-rays are taken to be scattered from individual atoms. Okay. The scientist von Laue examined the diffraction of X-ray in a more general way. He assumed that X-rays are scattered by individual atoms in a crystal. The scattered rays undergo constructive interference to produce diffraction maxima, and the maxima appears in some specific direction that obey certain conditions, and these conditions are known as Laues equation. Okay, and Bragg's law can be determined from Laues equation. Okay. Now suppose at the point A we draw an atom, okay, and at the point B we draw another atom, and they are separated by r vector. Okay, suppose at the point A there is an atom, and at the point B there is another atom, and they are separated by r vector. Okay, now suppose a parallel beam of X-ray is incident on A and on B. Okay, suppose a parallel beam of X-ray is incident on an atom at the point A and on an atom at the point B along the direction of unit vector n1 cap. Okay, so this is along n1 cap. So this ray is also along n1 cap, okay, because they are parallel. Okay. Now at the point A and B they are scattered. Suppose these are the scattered rays, okay, and suppose they are along the direction of unit vector n2 cap. So this is also n2 cap. Okay, so a parallel beam of X-ray is incident on A and B along the direction of unit vector n1 cap, and scattered rays are along the direction of unit vector n2 cap. Okay, so these are the incident rays along n1 cap, and these are the scattered rays along the direction of unit vector n2 cap. Now suppose this angle is theta, so this is theta. Okay, now we draw a perpendicular BM. Okay, we draw a perpendicular BM on this incident ray, and we also draw a perpendicular BL on this scattered ray. Okay, we draw a perpendicular BM on this incident ray, and we also draw a perpendicular AL on this scattered ray. Okay, so this is BL and this is MA. Now the path difference between the rays scattered from A and B is BL minus MA. Okay, so the path difference between these two rays is BL minus MA. Okay, so path difference suppose delta equals to BL minus MA. Okay, now we calculate BL and MA. Okay. Now to calculate MA, we see the triangle BAM. Okay. We see the triangle BAM. Now let us draw it. Suppose this point is B, this point is A, and this point is M. Okay. And this distance is R. Suppose this angle is psi. Okay. We consider this angle is psi. So in this triangle, cos psi is equals to base by hypotenuse. Okay. Here base is MA and hypotenuse is BA. So this is equals to MA by value of BA is R. So MA by R. So MA is equals to R cos psi. Okay. So MA equals to R cos psi. Now along MA unit vector is n1 cap. Okay. So along MA unit vector is n1 cap. So we can write this is equals to R vector dot n1 cap. Okay, according to vector algebra. Since along MA unit vector is n1 cap, so according to vector algebra we can write R cos psi is equals to here R dot n1 cap. So the value of MA is R dot n1 cap. Okay. Now to calculate BL, we see the triangle BAL. Okay. Now along BL unit vector is n2 cap. Okay. And this distance is R. So we can write similarly BL is equals to R dot n2 cap. Okay. So MA is R dot n1 cap and BL is R dot n2 cap. Okay. Now we put the value of MA and BL here. Okay. Now BL is R dot n2 cap minus MA is R dot n1 cap. Okay. So this is equals to R dot common n2 cap minus n1 cap. Okay. Now let n2 cap minus n1 cap is equals to capital N vector. Okay. So this is R vector dot capital N vector, where n capital N vector is equals to n2 cap minus n1 cap. Okay. So the path difference between these two is R dot n vector, where n vector is n2 cap minus n1 cap. Okay, so this is the path difference between these two rays. Okay. Now let's see what is n vector and let us draw it. Okay. Now this is n1 cap. Okay, and this is n2 cap, and this angle is theta. Okay. This is n1 cap, this is n2 cap, and this angle is theta. Now to draw n2 cap minus n1 cap, we extend this ray. Okay, we extend this ray. So this is n1 cap. Okay, so this is n1 cap and this is n2 cap. So according to vector algebra, this vector is n2 cap minus n1 cap, that is n vector. Okay, so this vector is n2 cap minus n1 cap, that is n vector. Now the magnitude of n vector is modulus of n. Okay, the magnitude of n vector is modulus of n. So this distance is modulus of n by 2. So this distance is modulus of n by 2. Okay. Now here we see that n vector is perpendicular to the reflecting plane. Okay. So here n is perpendicular to the reflecting plane. Now if we see the triangle, okay, if we see this triangle, then we can see that this distance is n by 2, mod n by 2, and this angle is theta, and this distance is modulus of n2 cap. Okay. So from this triangle we can write sin theta is equals to base by hypotenuse, perpendicular by hypotenuse. Here perpendicular is n by 2. Okay. So modulus of n by 2, and hypotenuse is modulus of n2 cap. Okay. So this is modulus of n2 cap. So sin theta is this from this triangle. This is equals to modulus of n by 2. Now the value modulus of unit vector is 1. So this is 1. So this can be written as this is equals to modulus of n by 2. Hence modulus of n is equals to 2 sin theta. Okay. Thus we get n is equals to 2 sin theta. Okay. And n is perpendicular to the reflecting plane. Okay. So this is n, and the path difference between the two rays, these two rays, r dot n. Okay. So this is the path difference. Now we know that the phase difference between the two scattered rays phi, phase difference phi is equals to 2 pi by lambda into path difference. Okay. We know that the phase difference between these two scattered rays 2 pi by lambda into path difference. Okay. Now here path difference is r dot n. So phase difference phi is equals to 2 pi by lambda into r dot n vector. Okay. So this is the phase difference between these two scattered rays. Okay. Now these two scattered rays will interfere constructively if the phase difference phi is an integral multiple of 2 pi. Okay. The phase difference between these two scattered rays, okay, these two scattered rays will interfere constructively if the phase difference phi is an integral multiple of 2 pi. So for constructive interference, we can write phi is equals to 2 pi n. Okay, where n is an integer. For constructive interference, phi is equals to 2 pi n, where n is an integer. So we can write for constructive interference, phase difference phi is equals to 2 pi by lambda into r dot n vector. This is equals to 2 pi n. Okay. For constructive interference, phi equals to 2 pi by lambda into r dot n. This is equals to 2 pi n. Okay. Now, if A vector, B vector and C vector are primitive translation vector of the point A with respect to B, then the position vector R can be written as R equals to A vector plus B vector plus C vector. Okay. If small a vector, small b vector and small c vector are the primitive translation vector of the point A with respect to B, then in terms of ABC, position vector R can be written as this. Okay. So for constructive interference, for constructive interference we can write phi A, phase difference phi A is equals to 2 pi by lambda into A vector dot n vector, and this is equals to 2 pi into suppose an integer h prime. Okay, phi A is 2 pi by lambda into A dot n, this is equals to 2 pi into h prime, where h prime is an integer, and phi B is equals to 2 pi by lambda into B dot n vector, and this is equals to 2 pi, suppose this is k prime, where k prime is an integer, and phi C is equals to 2 pi by lambda into C vector dot n vector, this is equals to 2 pi L prime. Okay, where L prime is an integer. Here h prime, k prime, L prime are integers. So for constructive interference, phi A is this, phi B is this, and phi C is this. Now if h, k, L are Miller indices, then h prime, k prime, L prime can be written as, in terms of h, k, L, as h prime is equals to suppose an integer n into h. Okay, h is Miller indices, so h prime can be written as an integer into h. Similarly, k prime can be written as n into k, an integer into k, and L prime can be written as an integer n into L. Okay, so h prime can be written as n into h, k prime can be written as k into n, and L prime can be written as n into L. Okay, so here we can write this is equals to 2 pi n into h, and this is equals to 2 pi n into k, and this is equals to 2 pi n into L. Okay, so phi A equals to this, phi B is this, and phi C is this. Okay, and this is n vector. Okay, here we see that this is n vector and it is perpendicular to this reflecting plane. Okay, now suppose the angle between A and n is alpha. Okay, suppose the angle between A and n is alpha, and the angle between B and n is beta, and the angle between C and n is gamma. Okay, we consider the angle between A and n is alpha, angle between B and n is beta, and the angle between C and n is gamma. Then now if we see this equation, okay, this equation can be written as 2 pi by lambda into A dot n vector is equals to 2 pi nh. Okay, we write this equation. Okay, now here 2 pi will be cancelled, or A vector dot n vector is equals to nh lambda. Okay, now the angle between A and n is alpha, so we can write A modulus of n into cos alpha is equals to nh lambda. Okay, now the value of n is 2 sin theta. Okay, value of n is 2 sin theta. So if we put the value of n is 2 sin theta, then we get or a into 2 sin theta into cos alpha is equals to nh lambda. Okay, so we get 2a sin theta cos alpha is equals to nh lambda. Okay, so if we simplify this equation, we get this, that is 2a sin theta cos alpha equals to nh lambda. Similarly, if we simplify this equation, here angle between b and n is beta. Okay, so if we simplify this equation, we get 2b sin theta cos beta is equals to nk lambda. Okay, and here in this equation the angle between c and n is gamma. Okay, so if we simplify this equation, then we get this is equals to 2c sin theta cos gamma is equals to nl lambda. Okay, so these three equations are known as Laues equation. Okay, so these are known as Laue equation. Okay, this set of equations are known as Laues equation, and it represents the condition for diffraction to occur. Okay, the condition for diffraction to occur. Now if we know the value of n, h, k, l or lambda, okay, if we know the value of n, h, k, l and lambda, then the value of alpha, beta, gamma or theta can be calculated from these equations. Okay, if we know the value of n, h, k, l, lambda, then the value of alpha, beta, gamma and theta can be calculated from this set of equations. Okay, so this is Laues equation. Now I discuss how Bragg's law can be derived from Laues equation. Okay, so Bragg's law from Laues equation. We know that if D be the interplanar spacing between two planes, okay, if D be the interplanar spacing between two planes, then we know that D is equals to A by H cos alpha equals to B by K cos beta equals to C by L cos gamma. Okay, we know that the interplanar spacing D between two successive planes is A by H cos alpha equals to B by K cos beta equals to C by L cos gamma. Okay, now if we take this relation, that is if we take D equals to A by H cos alpha, then we get here H equals to A by D cos alpha. Okay, here H is A by D into cos alpha. Now if we take first condition of Laues equation, okay, if we take 2a sin theta cos alpha equals to nh lambda. Okay, we take first equation. Now here we put the value of h, okay, or 2a sin theta cos alpha equals to n, and value of h is a by d cos alpha into lambda. Okay, here cos alpha and a will be cancelled, or 2 sin theta is equals to n lambda by d, or 2d sin theta equals to n lambda. Okay, 2d sin theta equals to n lambda, and this is Bragg's law. Okay, this is Bragg's law. Okay, thus I discuss Laues equation, and from Laues equation I derive Bragg's law. Okay, thank you for watching this video.